All right, guys, welcome back. Hopefully everybody had a good reading week. We got 13 more lectures for the semester. So we basically just gotta keep developing our bridge controller until the end. Time permits, we might be able to talk about some new example for refinements. If not, I can also give you some practice question, maybe toward, for the exam. So either way, you can also see the material. But for today, as I make an announcement yesterday, I'm just going to cover some new materials for the first half, maybe about 40 minutes or so. And then we take a short break as usual, taking attendance. And then we get the remaining up to 40 minutes to answer your question. So if you just want to go over, for example, the practice question, you're more than welcome to still ask me. That's okay. But I also posted like a review session from last year, basically going over the same set of questions. So if you want to kind of save time, ask me something else, for me to repeat certain parts of the lecture, maybe that'll be a better use of your time. But you can decide. It's really your time. I don't mind either way. All right, so let's now, quick reminder. Your programming test is still being graded. I already passed all the submission to the TA, and then they are BC grading. They should really get back to me about early Friday this week. And then I'll just take over the weekend to finalize the result. I should be able to get back to you, hopefully before Tuesday's class next week. And once you receive the result, we will not actually return back the questions or your submissions. So if you got any doubts, take a look at the feedback file you're going to receive. You can definitely submit a regrading request, in which case either myself or the TA, they will take a look again just to see if there's anything that might be a mistake from our end. We can take a look. Or if you want to go over certain parts of your submission, you can also make use of my office hour. You can go all the way until this, at the end of the semester. For that part, there's no deadline. You can still talk to me, even before the exam. Okay? All right, so for tomorrow, it's going to be your written test 1. It's going to be over E-class, so please do check the guide for the PDF, right? So you're going to use the, make sure to bring your mobile phone, and then you're going to use the dual mobile to really log in. And that will start just the same time. Like last time, okay. And I think that'll be it, right? But we'll talk more, maybe in the second half of today. Any questions about the course in general? Yes?
Will the event be, programming test be marked by if it runs, or is it like how much you manage to put in?
Right, so how about this? Maybe after the result is actually released, once you see the feedback file, you'll see a very clear breakdown about exactly what's being run. So maybe at that point we can clarify the points. Because for me to actually clarify, I'm going to do something from scratch. It's going to confuse everybody, right? Okay. Why don't we do that after the results are released? Okay, thank you. Okay, let's do a quick recap from what we covered before the reading week, and then we'll cover some new stuff. Yeah, let's see how much we can do. Okay, so before the reading week, we basically just spoke about how you can somehow visualize your model as a transition system. So abstract state machine, basically ASM, abstract state machine. You can see also the term in the slides. So starting from some initial state, you can gradually think about for each state whether or not a particular event's guard is actually enabled or evaluated true. If the event's guard is true, you can definitely have it take place and then apply the updates. It's definitely one very nice informal way and visual way to really build out the state machine. However, it's not going to lead you very far, because once the example gets big and you have so many possible events that might happen, you don't really want to do this manually. So once you guys maybe go to 4315, for those of you who will continue with the stream, so there will be a way called model checking, which is going to build this kind of graph automatically. There will be a tool to do this. You don't need to do it manually. You just need to have some basic understanding. Okay? So I would say this one here is really for your information. Sometimes for a very small scale example, you may actually want to visualize your system this way. It's also actually very nice to build the intuition. Okay? And that's just another example, right? Just about evaluating the guards and also evaluating the invariants. But for this course, what we do is we want to turn everything that we want to prove into proof obligation. I think today we'll do a little bit more, and when we resume the class on Thursday, I'm going to dive deeper into inference rule. That is definitely something you will have to also get familiar with. We'll see if we can get some basic introduction today about inference rule. And we talk about before and after predicate. I want to do one more example, maybe a little bit related to your lab number 1, just to draw more connection. Okay? The idea would be, think about every event we are taking either ML out, ML in, withdraw, deposit, transfer, any event. They are more like a state transition. So when the event is first, whether or not the event should be even enabled. Think about a particular state where you're going to enable, starting from a particular state, you're going to evaluate if the guard for the event is actually true. If it is true, this can be called a valid pre-state. And then the action for the event is going to take place, updating some variables, etc. And then you're going to get something called an after state or post state. So pre-state and post states. I'll do one more example today after the recap, just to hopefully reinforce the idea a little bit. Very important to know about the idea about before-after predicates. Later on, when we actually want to come up with a precise proof obligation, we have to use the before-after predicates. So very simple one is, let's say here, ML out. So we say n, the post-state value becomes the pre-state value of n plus 1. And the before-after predicate would just be right here. n prime, which is the post-state value, equals n plus 1. Before-after predicate is just like a true or false. So whenever you got the same variable, but with the prime, that simply denotes the value that happened after the transition. Right? Just get used to that notation. You're going to see that a lot. So for the same variable x will be the pre-state, and x prime will be post-states. Right? And then we talk about the swap example. This example here just to show to you, if you got things like this, like this might be something you kind of wrote before, maybe in 1011, maybe 1021, back in the first year to see how you can swap the value of two variables. This will be valid if you're doing that in MATLAB or Java because things will be evaluated sequentially. However, this is not what rodent really means to really have when you got three separate actions. So things will actually be done simultaneously. So you're only supposed to mention each variable only once. And then you should not really assume there's any sequence between them. So the best way to think about it is, think about this one here simply correspond to this particular predicate, before-after predicate. The after state value for temp is going to become the before state value for x, and etc. So you basically got 1, 2, and 3 conjoined together rather than one executed after another. So there's a very important difference to make, right? So the final solution for swap would be just as easy as this. Of course, if you're implementing this in Java or C# or C++ or Python, this will not be the way to implement. We know that pretty well, right? So just distinguish between modeling in event B and also implementation in your programming language. So they're different. Okay. Any question about this? Yes.
For example, for any single state, what if there's like more than one event and the guy is available for more than one event? Which one do you consider? How do you predict it?
It's a very good question. Let me just clarify this a little bit more in a more intuitive way. The question goes like this. In a particular state, let's say we got more than one event available, enabled. Let's say this is a state. Let me call that maybe state 1. And of course, we're going to evaluate different variables. It could be variable 1, variable 2, variable 3, etc. Okay? We're going to evaluate this, let's say, hypothetically. Let's say at this particular state, let's say event 1 and event 2 are enabled. One thing for sure, we cannot have two events happening simultaneously. That's not allowed. Right? Only one event can happen at a time. Only one event can happen at a time. Can happen at a time. So that means think about there are two alternative universes for this particular scenario, which means we may have one possibility where E1 is going to take place. Another possibility would be when E2 takes place. So what do I mean? So the way to think about it is like this. So here we got scenario number 1. We still got our S1 where E1 is enabled. In that way, it's going to end up in maybe, let's say, S2, let's say. And then we still got the same S1 for the same state because E2 is also enabled. In that case, E2 may take place for its action, and this might end up in a different state, which is S3. So we got two possibilities. They happen kind of in parallel. They don't really happen at the same time. There's two possibilities. But you can think about this as one possible post states. So this is another possible post states. Now the principle is both of them must satisfy the invariance, meaning that starting from S1, either you take E1 or you take E2. Both post states must satisfy all the invariants still. Okay, that's the principle. And you will see that later once we figure out all the proof obligation that we have to study, they all cover this, right? You don't really have to worry about whether, what are the possible combination of the interleaving of the events. You don't really have to. Okay, so let's say, okay, let me just conclude about this little example here. All possible post states must maintain the invariance. Does that answer your question?
Yeah.
Good. Very good. It's a good question, actually. I'm glad it's asked. All right, and then we spoke about invariant, excuse me, we spoke about invariant preservation. So this is just like an intuitive, like a predicate. For every possible states, we got to make sure if the state satisfy all the typing constraint, then it must satisfy the invariance, right, intuitively. Okay, that one's okay. But if you want to find some weakness, which we'll see some exercise maybe a little bit later, if we can see that potentially the invariant might be violated, how can we find some weakness? We'll see that. Okay. All right, so this is something also very important. We talk about sequence, okay, sequence calculus, sequence. I'm not too sure if I will be able to get to that point today, but you will see something with a very similar syntax. So that's something we'll see either today or Thursday. Okay, it's called inference rule. But for the sequence, just remember, you can either present that horizontally or vertically. And the symbol here is called turnstile. Okay, so every sequence can be interpreted or formulated as an implication. So when I say H, the hypothesis, entails the goal, G, that means I'm trying to prove something. I'm trying to prove that this particular implication, H implies G, is true. Assuming that H is true, can I show that G is provable? Right? That's something I want to prove. Okay? And we spoke about what does it really mean when the hypothesis or antecedent here is simply just empty. That simply means it's true. It cannot be false. Because that's false, then you got nothing to prove. Everything is proved automatically. Okay? It's not appropriate. All right, so please review the syntax and also the meaning for the sequence. So for your written test number 1, you don't have to worry about this part for the bridge controller. But definitely for your written test number 2, you will actually have to worry about how to formulate sequence and also how to prove them. Right? Okay, that's about sequence. And then that's the last page we did before the reading week. So this one here, just to show you a little bit informally, you can see all these guys over here, so they are kind of phrased in English terms. In some way, they are intuitive enough to tell us what we should really put. But we're going to see something a little bit more formal today, just to see the different components that should be in the proof obligation. We'll see. Okay. So in order to show that the invariant is really maintained, so this is turnstile. So what do we want to prove? We want to prove that the invariance in the post states, basically after the transition of the events, some events, the invariant is actually maintained. It should be evaluated true in the post states. What can we assume in order to do this proof? We can assume about all the axiom. We can assume the invariant itself before the transition in the pre-states. And also, whichever event we are trying to prove that maintenance, every time you want to prove that the maintenance of invariance, you focus one event at a time. You don't try to prove two events at the same time. So that will be the guards for some events. So we'll have something called ML out and something called ML in. So this was like a very informal, like a sketch, like last time, just a first introduction. So when you review this particular page, focus more on this particular part right here, right? So let's look at that more closely. I say n prime is a member of natural number. And also n prime, again, less than or equal to d. So the way I kind of phrase this predicate here, I use all the post-state value whenever necessary, whenever applicable. So this one here is really corresponding to the two invariants together, except the n here, I'm really trying to prime them to emphasize they really denotes the value in the post states. So that's really about the invariant evaluated to be true in the post states. But when you actually want to discharge the proof obligation, you don't really leave the prime here for manipulation. This might be a good first step just for you to see. To simplify that, you have to somehow substitute every occurrence of the prime variable using the before-after predicate. So here we know that we are talking about this particular MLR events. And we talk about its before-after predicate for its events, for its action. So this one here, n becomes n plus 1, simply correspond to n prime equals n plus 1. So that means every occurrence of the post value n prime can be replaced by n plus 1, right? So that's why we simply replace this one here by n plus 1. Also replace this one here by n plus 1. That's what we did, right? So the overall proof obligation would be something here together with something this, right? With the turnstile. We're going to do many exercises like this, but that was just the first one. So focus more on knowing that, number one, you want to get an initial draft version using the prime version to talk about the post states. And then you have to get rid of all the prime version of the variable by applying the before-after predicates. So that's really the goal. All right? Might be a little bit tricky if that's the first time you're seeing it, but I think it's not too bad once you just do more practice. Okay. All right, guys, any questions? Good? Okay. Let's now do one more example about before-after predicate. Okay, let's take a look at that very quickly. Okay. So let's now revisit one of the events we did in lab number 1. Let's say we do the withdrawal events. Okay. And I want to speak more about, just give you one more example about the invariant maintenance. So let's say transition of n events. Okay, let's say the event we're talking about, let me just put down the rodent code or specification. Let's say we got our withdrawal events. And then we got two parameters. We got a member of the account, assuming that account is a carrier set. And also we got the amount, which is a natural number. Okay. And then there's some constraint about the parameter where A must be a valid account. It's in the domain of B. Remember, B is a balance function. Okay, let me remind you very quickly. So B is actually from the account partial function to integer. Okay, it's a quick reminder. Okay, that's back from your lab number 1. Okay, and then we have the action. Begin and also end. And of course, this one here is very straightforward. We simply say B, the balance function, is replaced by another function. And the function will be almost like the same as before, except we're going to modify just the mapping for account A and make sure its balance is deducted by exactly V. Right? That's something we're going to do. Okay, so we can say B overridden by, and we can say A maps to B of A minus V. Right? For the logic part, I'm going to omit, right? So that's the part you kind of studied before, so we don't need to revisit. Okay? So think about this part over here is the effects. Oh, sorry. This one here. So this one here is really the effects of the events. Okay? So let's think about what's the before-after predicate right away. So the before-after predicates, B prime is equal to the B overridden by just the same. A maps to the pre-state value of B, A minus V. So you can see this is the post-state value for the balance function. Will be the same as the pre-state, except the balance for A should be updated, should be decremented, right? Before, after predicate, right? Let's put one more thing into context, and then we'll talk about how we can formulate certain things, okay? So now, let's think about with the invariance. Invariant I, okay? Invariance. Let's say the invariance defined as for every A is a valid account in the domain of B. The B of A should be, let's say, larger than or equal to some credit limits, right? That's also something we saw earlier, assuming everything has been declared properly as before, okay? Okay, let me just highlight this, invariance. All is good. All right, let's now think about how we may actually understand about invariant being satisfied in the pre-states and also invariant maintained in the post-states. That's something we want to see. So let's now, first of all, let's draw a diagram quickly. So we have some pre-state over here, and then we have some post-states. So this will be some pre-states. Let me just use right here. Pre-states. And after the transition, we're going to have some post-states. And the transition of the event we are thinking about is withdrawal. Okay? Withdrawal, right here. All right? In order for withdrawal to really take place, the guard must be true, right? So to start with, we know that withdrawal must be enabled. Evals to true, that's for sure. And then after that, we want to make sure here the invariance maintained. Or you can think about, this is important, think about I here, I'm just going to somehow express as a prime. Prime in the sense that the I expressed all in terms of the post-state values is going to evaluate to true as well. So I here, think about I here must be true. And also I prime over here must be true as well. All right, let's see how we can express that, okay? And I'll try to keep them in the same page. So you can definitely see. Okay, let me just move this guy a little bit to the okay, how about here? Okay, let's now do a sequence right here. Let's now see how the sequence is going to look like right here. Oh, sorry. Let me do it again. Okay, that's good enough. I'm going to write something very similar to what we did earlier before the reading week. Let's see what should be in the antecedents and what should be in the consequence. All right, let's see that, okay? So over here, we know that, let's put the turnstile first. The turnstile is going to be right here. And then we know that, let's ignore the axiom and also, okay, just ignore the axiom, okay? There's some certain axiom which we don't have to worry about for this example here. So you can think about, there will be some axiom. And then also for the guard itself. Okay, so the guard for the withdrawal. That one is going to be A should be in the domain of B. Okay, so that's the axiom. Sorry, that's the guard. Okay, let's now put things here. We're going to put the invariance should be satisfied in the pre-states. And also, the invariant should be satisfied in the post states. Now, what should they be? All right. In the pre-state version, very straightforward. That one there, I can replace it by, for every A in the domain of B, and then B of A larger than or equal to minus C. That's good. What about I prime? I prime here, because we know when we actually try to do this withdrawal events, we are only changing B. This is the only variable being modified. The only variable modified. That means when we want to come up with the I prime version, we just have to make sure every occurrence of B is going to be replaced by B prime. Okay? So what do we do? So over here, you can just before after predicate, basically. So now let's see here. It's going to be replaced by, for every A, it's a dummy variable, we don't need to prime it. And also A in the domain of, now, B here should be B prime. Imply B of B prime of A larger than or equal to minus C. Okay? So the main difference is right here. B prime and B prime versus B and also B. All right? I'm just trying to do the example in a slightly, just doing the same rule like what we did before the reading week in a slightly more complicated expression, right? And normally this kind of expression will be done automatically, in Rodin. But I think for us to understand what's going on, it's worth doing, just manually. So now a question for you. How do we simplify this? Because the final form, we should not have any prime. What should we replace B prime by? Would you agree it should be this expression here? Okay. Think about what we did earlier. Earlier, before the reading week, we said that replace the M prime by the M plus 1, the right-hand side of the before-after predicate. Right here, we're going to do something similar. Okay. So here, what we do is we're just going to, that's the final bits. So this is basically the final bits. So replace this part over here by B overridden by expression. And replace this one here by B overridden by this one here. So we're basically saying the post-state invariance is going to be for every account that's in the balance function, but the balance function has been already updated with the account A mapping to some decremented account, that decremented balance right here. Okay, that's what we have. Okay, just doing substitution. Right? Any questions about this? Go ahead.
Yeah, I felt like because now your quantifier is using A, right? But in your overriding, you're also using the same A. Does that
Oh, I see what you mean. It's a very good point. Yeah, I shouldn't really do that. Okay, that's a very good point. So I think maybe let me, okay, you made a very good point. Of course, let's say if for any machine, like a Rodin, when they do it, they might just do some renaming automatically. Maybe by renaming the dummy variable A by some other variable. But let's just change that just to avoid confusion. Let's say here, maybe easier if I change the dummy variable. So rather than A here, what about I just say X? X and also X. So this will be X over here, and this will be X. X, X, X. So guys, I hope you see the issue, right? So I just have some name clashes, okay? Because you can see the parameter A somehow clashes with the dummy variable I chose for the invariant A here. I just rename it to be something different. For the dummy variable, you can call it whatever name you like. Okay. So this page here, basically we're doing, just let me recap, and then we can move on. This one here is really just trying to do the same kind of exercise by replacing the post-state version of the invariance by using some right-hand side of the before-after predicate. It's just that used to be n plus 1. But now the before-after predicate tells you that the right-hand side is something just more complicated. You just got to do the substitution. That's all you got to do. Okay. All right. Think about it, and then let's now move on. Okay. The next part there is going to be a little bit tedious, but I'll try to move it as quickly but still clearly as possible. We'll just have to introduce certain components that you're going to see in lots of the proof obligation. It's going to essentially define formally in the slides. I just want to make sure you understand the notation. Okay. So this one here, let's see. It's going to be slide number 18. Okay, let's now define the different component. And at the same time, I'm going to use this model we have over here to really exemplify the components. Okay, let's now go one by one. So having this model here, we got different components that we want to kind of use as some formal symbol to denote, so that we can refer to those components using those symbols in the proof obligation. Okay, the first one. So we have a little c, lowercase c will be the list of constant. Okay, let's start with that. So the first one is right here. So the c here is the list of constants. And you can see the constant is this section over here. It's a list. So you will see you will say that little c is defined as a list containing just d. Okay. So just in case you're wondering about, this symbol here is defined as little c. So whenever you see any lower c in the proof obligation definition, it simply means all the constant. Okay? So here we just have one, so it's a singleton list. All right, the next one. After the constant, we also got axioms. So the axiom here goes like this. It's capital A and with C. A here is more like a function. It is saying, given a list of constants, I want you to return back to me the list of axioms you have in the model. Okay, I'll put it down first and then I'll give you an example. So the A here is a function. On constants. Because you can see that here, the C is exactly the C over here. We're just using capital A to say, given the list of constant, I want to return a list of axioms. So what will be the example? So here, we have axioms. So now, let's be careful. A here, and then in this particular model, we have a singleton list of the constant, just D. All right? That one there is going to give us all the axiom. And here, you can either try to maybe list exactly the predicate, or you can use label. So here, for example, you have the label of the axiom. So again, just one single axiom. So it's a singleton list. It's going to be a list of the labels of all the axiom. These will be axiom 0, 1. Oh, by the way, maybe that's something I didn't quite mention when we first look at the naming. So when you look at, for example, okay, that one there, I can just do that quickly. When you see the naming, so there's a naming convention here. So the 0 here simply means it's model M0, the very first model. So we are defining some axiom just for model 0. Okay? And then the 1 here is simply a way to index the axiom starting from 1, 2, 3, 4, 5, etc. Okay? Because, for example, here you can see for invariant, you got 1 and 2, right? So this is the index of the axioms. Yeah, you will see similar naming as well. So for example, later on, once we finish the first initial model, when we get to the first refinement, it's going to be M1. In that case, this number here will be just axiom 1 underscore 1, 2, 3, 4, 5. Okay. All right. So that's about the axiom. And then next one. So let's talk about V and V prime, right? So pre-state and post-state. Okay. That one should be also quick. So let's now talk about it. So we got pre-state value. Oh, sorry. We got pre-state value right here. And also we got post-state value. We got pre-state value. And also we got post-state value. Just the prime version. Okay, let's see example here. So you can see here we got variable section right here. So variables in the pre-states. We'll say V will be, again, a singleton list because we happen to have only one variable. So the list contains just N here. And then we also got the post-states, V prime, which will be the list. And here, corresponding to N, we actually got M prime. Okay. So this one here is the pre-state. And this one here is the post-states. Okay, this one here is straightforward. And then let's now move on. Okay, and then invariance. So now if you look at the invariant I here, that one is also a function. Okay, I want you to compare axiom and also invariance. So if you look at the invariant here, I. Okay, so now let's look at these two closely. When I define the axiom, I only got C. When I define the invariance, I got both C and V. What does that mean? That means when you define axiom, you actually only include the constants. But when you actually declare like an invariance, you only include both the constants and also variables. Okay, that's what it means. Okay, so now in our case, so the C over here contains just the constant D. And then we have the V here. Also, we have the variable N. You know what? Let me just use just orange. I think that should be okay. That one there, just the variable. Okay, list of invariants. Let's now see some example. You can see for the invariance here, the 0 here simply means we got model 0. And then we also got 1 and 2. So 1 and 2 here are just indices for the invariant. I can refer to invariant number 1, invariant number 2. And let's now write them out quickly. So I can say invariance, first of all, the list of constant, and also the list of variables. Right? And then we're going to refer to is a list of invariant. In this case, we've got 2. So it's going to be a list of 2. So that one there is going to be invariance 0, 1. And also invariance 0, 2. All right. Now, sometimes you also see some variance to this particular notation, right? We might be able to somehow add some suffix to here, like a subscript to it, okay? I'll show it to you. So for example, you might say something like, I want to get invariance, but only I want to get the first one. So I put the index there. And then that one there is going to give me, again, I am going to use the constant and also the variable. That one there, rather than is going to give me the list, it's going to give me a single one. And index 1 is just referring to the first one. Indices start with 1, not 0. Invariance 0 and 1. All right, so here I just have some index. Index here, and then That's the 1. Okay, halfway, almost there. And then next one. We have the guard. So the G here is simply is kind of relative to every event. We have a G function. Okay, it's just about the guard. So let's see this one here. Let's say for the guards. Again, the guards over here may refer to both the constants and also the variable. The constant will be just the D, the variable will just be the N, right? Just a G function, okay? So let's see example. ML out right here, for this particular event, the G over there, where we got the constant D and also variable N, even though it's godless, but it's just equivalent to true. So we're just going to say true. A single one. And similarly, for MLN, it also has a guard function. We have D and also N will be also true. But later on, we're going to fix the guards for each of the MLL and MLN. So the guard is going to change. Okay, but for now, just live with what we have right now. All right, 2 more. The next one here. So E function just about the effects. Effects is basically the right-hand side of the before-after predicate. For example, what we saw earlier. Okay, you can think about for this particular event, this is the before-after predicate. This right-hand side is the effects of the events. Okay, and for this earlier example, the right-hand side n plus 1 is the effects, right? Just the right-hand side. Okay, let's see how that's going to work out. So for the effects, right here, or you can think about it's the right-hand side of the before-after predicates. And whenever you talk about the effects of an event action, you can refer to constant, which will be D. You can also refer to the variable N. All right, let's see example. For ML out, this is the effects. So we will say E, taking the constant, taking the variable, is simply N plus 1. The reason that this should be a list is because sometimes for a single action, you may have to modify multiple variables, in which case each one should be at a particular index in the list. Okay. Similarly, right here, N minus 1 is also the effects. Taking the D, taking the variable N, that will be N minus 1. It's a list with just N minus 1. All right. The final bit right here. That one there is about before-after predicate, right? So before-after predicate basically take the right-hand side and put the left-hand side as a prime version of the variable, and that's it. All right. So let's now just take a look at this. So the way we specify that is like this. This is the before-after predicates. This one here. So this is the before-after predicates. And you can think about the V prime here is a post-state value. So this one here is the post-state value of the variable. And this part here, the E that we spoke about, that's the effects of the action. E here is the effects of event action. All right, let's see 2 more examples. Okay. How do we figure out the before-after predicate for ML out, for example? Let's say here, right? So that one is going to be, so before-after predicates. M prime which is the v prime here, right? Just the list of variables, but with the prime. And that one there is equals n plus 1. So we are saying that n prime is going to change to n plus 1. That's what we are saying, okay? And this one here, for m out n, the before-after predicate is going to be also n prime. We're also modifying n. That's going to be the effects, n minus 1. Okay, one more, and then we should take a short break. Okay, and then we'll talk about your written test 1. I think that's all we can do today. Let's revisit very quickly our swap events. If you recall the swap, so we have begin and also we have the end. So we got x, y, and y, x, right? That's what we have. So if you think about the effects, the effects over here, let's say there's no constant. And we only got two variables, x and y. And effects is going to be basically x is going to be changed to y, and y is going to be changed to x. So the effects can be actually contain two variables. You got two multiple values. So what should you really do from this page over here? I would say just try to keep this as a reference point, because later on you're going to see this kind of a component like a CAVI in the actual formal definition for the proof obligation. Keep this as a reference point in case you don't know what the symbols really mean in the proof obligation. You don't really have to memorize them, but hopefully just get used to them. Okay. All right, any questions? All right, why don't we take a short break, and then I think after the break, we still got half an hour to answer your questions. Okay. All right, guys, we got about 27 minutes-ish. Any questions? Apart from asking me what's on the test. I can tell you that I'm still finalizing the questions. How about this? Let me see if I can recall anything that might be useful to you. You may want to review about visualizing the various kinds of a relation, like a relation, partial function, injective function, etc. We did quite a bit of visualization in the class. That could be useful for tomorrow. Okay, and then I think for your, I think that'll be fair. Since you really did the practice test, if you haven't, you may want to do it as soon as you can. I think the question 1, this kind of question here, okay, about deciding whether it's a theorem and whether you can prove or disprove properly, by some witness, right? So these two could be useful as well for tomorrow.
Can I ask right now?
Go ahead.
Okay, and my first question is that, given tomorrow's time is like 1 hour and 20 minutes, right? So
No, it's 50 minutes.
50 minutes.
It's set in the guide. It's actually, because your lab is only 50 minutes.
So is that from, for example, my first lab is from 1 o'clock to 1:50?
No, please check the guide, right? It's like your programming test. Yeah. The first one is from 1:30 to 2:20. Okay. 50. And then for 2:30 to 3:20, okay. Right?
So given that the sample test has a 5 question and a half an hour time limit, does that imply it's gonna be like double because the time is around?
Yeah, I don't want to say it, but as I said in the beginning of the actual page, right? So that one, they just let you get used to the format. Okay. It doesn't really tell you. Don't want to think too far, right? I would say take the practice test, get some expectation about the format of the test, and then make sure you study the materials. That would be the way to go.
Yeah, because the time I spent on my practice question, it was like pretty relaxed. But however, in the actual test, are you gonna give me the answer to say that it's gonna be much more time spent wise on each question?
Well, basically got 50 minutes, right? So I put the question there. I think that's appropriate for 50 minutes.
Okay.
That's all I can say, right? Yeah.
All right.
Yeah.
I will let my colleague.
Okay. Yeah, go ahead, please.
If there are minor errors within your answer, like
Yeah.
for example, an extra pair of parentheses or a curly bracket instead of a round bracket, are we able to afterwards go to a TA to try to get it reassessed, or will it always just remain as 0 out of?
Oh, okay. You mean there might be some question there, the answer might be auto-graded by E-class. Maybe it says, let's say your answer maybe got no parentheses, but the answer got parentheses. I think I'm open to some talk. How about that? But I would say, of course, you want to avoid that in the first place. You want to read the question carefully so you can answer as accurately as you can.
I'm saying it's a case of typos or a fat finger.
Yeah, I would say I definitely can understand that, but I would say I'm open to discussing it. It also depends on how far the answer might be from the actual solution, right? We can talk. How about that? Okay. I wouldn't say you definitely get a marks back, but we can definitely talk. Okay. Yeah, question.
So given my first question would be that since you have mentioned such a phrase in your lab test, least accurate and most accurate, how should we interpret that? If such a phrase appear in the in the programming in the written test model?
Okay. So let's say this. So when we say things like least accurate and also most accurate, so you can think about basically both descriptions saying they're both basically correct. Under the assumption that your answer is correct, but you may want to think about which one is closer or like more accurate about the relation. Let's say, for example, remember the visualization, right? So if I have something like this, let's say I have, let's say we got total function. Okay, and then we got the bigger one, which is a partial function. Okay, we got another one, which is a relation. Okay, so this might be the kind of visualization you want to review. Okay, for tomorrow. I think there's some question that kind of related to that. Okay, not exactly this, but it's kind of related. So let's say this: if I have a member right here that's happened to be a total function. Okay, so it is correct to say that any function here, to say that it is a total function, also is a partial function, and also it's also a relation, right? They are all correct because it's a member. Okay, so now in the case of least accurate, most accurate would be choose the smallest confinement where you're going to find that particular member. In this case, the most accurate would be just the total function. Most accurate, right? Most accurate would be S total function T. And the least accurate would be, in this case, relation T, right? That's what you rather meant. Yeah.
Okay, so can I add on?
Yeah, go ahead.
So given that the relation need to be a one, for example, it need to be a 1-to-1. At this case, will you still see that this accurate would be a relation that allow it to be non-function? Yeah, that's my question.
Yeah, so, okay, don't get it too complicated. I'm just saying that if I'm given a particular, it also depends on the phrasing of the actual question, right? You're more talking about what we had in the programming test. Yeah. The format could be a little bit different from the written test, yeah. Right? So I'm just saying that if you know that the particular function you're considering really belongs to this particular category, in that way, it is correct for you to say that one there is a total function. That one there is also a partial function, that's also a relation. But which one would be the most accurate and also most appropriate modeling choice? This one here. Most appropriate.
Exactly. It's my fault. Thank you.
Yeah, good. Okay, go ahead.
So what if there's two that have the same priority? So let's say there's a function that's surjective and injective but not total. then would you say it's
Yeah, of course, you know, there might be cases where maybe it's really hard to say which one should be, has more like a weight in terms of accuracy. So this one just, in this case, is kind of obvious. You can draw the diagram accordingly. So it really depends on the case.
So you just have to like assess which one would be.
Yeah, assess, yeah. Okay, sorry, I didn't keep track. So go ahead, okay, yeah.
It's more related to like the actual course content, but like where would surjection and injections be like in this diagram?
Injection, surjection.
Yeah.
I think that one there, yeah, it's really hard to see exactly, right? Because injection, surjection itself can either be total injection and also partial injection, total surjection, partial surjection, right? It's really hard to really have a single diagram where we're going to visualize everything over there. It's more like a relative. So when I only compare this, this, and this, it's kind of easy to put these three circles over there. But when you actually got many different types of function there, sometimes they are not exactly related, right? So they talk about different aspects of the either domain or range. So I would say just try to focus on the ones where it's kind of obvious, well, at least the one we talk about in the lecture. Yeah. Good. Go ahead.
I had a question regarding the event B summary.
Event B summary, yeah.
Yeah, so are we given that?
Okay, good. Yeah, I'm glad you asked. The policy will be the same as before. I'll put it here, right? Just make sure it's written, okay? So for the event B summary, so you have choices. It will be placed on the desktop, I believe. When you log in to the E-class, right? You can definitely go to activities and go to files and you will see under desktop or under home directory, either way. The same place. And also you can feel free to bring your own copy. Okay, bring your own copy. However, please make sure that one there, you should not try to sketch on that during the test. That one got to be 100% clean. Okay? But if you bring your own sketch paper, you can sketch whatever you like on the sketch paper. Okay? Okay? Not to be sketched. So basically the same policy as the programming test. Yeah. Yeah.
On the test, should we expect the format to be most like the practice questions that you gave us, or are we going to expect some questions similar to the programming test where you kind of give us a requirement in words and then we have to make an...
I think the format is going to be more like a multiple choice. So maybe you're given, sometimes maybe the multiple choice is more like a radio button. You got only one single correct choice. Or it could be there might be multiple correct choices you're going to choose, right? And also there might be, I believe there might be another one, which is also on E-class. You somehow have to rearrange about the different answer, but that's something you will see, yeah. I would say the practice test definitely kind of expose you to quite a bit of formats already, yeah. Mm-hmm. Yeah?
So apart from like the math review sites, is there anything else that would be like helpful for us?
Sorry, say it again, I didn't hear.
Like the math review sites you told us to look over? Is there anything else we could look over?
Oh, anything else? You definitely have to, okay, you know what? I don't want to say anything wrong. Okay, let me just take a look. Okay, so if we look at the guide, okay, sometimes I might contradict myself, so I want to be consistent. Okay, if you look at the guide right here, so you will see that, okay, format is about multiple choice, right? That's something I just said. And then, oh, another hint for you. So remember in the math review slides, we kind of went over 2 slides about the modeling decision. I think the first one is about that location, like where it is, right? We talk about whether that should be a relation, should be a partial function, should be a total function. Review that slide could be useful. And then also the modeling decision in the final slides, when we talk about how you can formulate an array, that can be also useful. So the idea will be whenever we got any natural language description, what should be the most appropriate modeling decision? There could be a question like that. Okay? Now, of course, to really answer that kind of question properly, you have to review the definition, right? Make sure you're clear. Okay, so let's see this. Okay. Let me just be sure. right? Lab 3 is not even released, so of course you don't have to worry about Lab 3. So I think the most important thing will be the math review slides, that's for sure, right? Make sure you go over them and make sure you're familiar with the definition, the case, the example we did. And you may also want to go over briefly also about Lab 1 and Lab 2, just about the solution itself. You don't need to redo or enroll them. That's not going to be the purpose for the test. Yeah?
So there's a question about the modeling of array slide at the very end. Because I remember there was a distinction between int as in, like the set of all
integers, yeah.
and then integer as in like the Java class.
Right.
Do we have to make that distinction on the test?
Yeah, so you can think about in the test, right? That's a good question here. So you really have to interpret that literally, you know, like what I write. So for example, if I say, okay. If I say something like array A, and then I might say indices, natural number, partial function. If I say this, I really meant the set of all integers. That's really what I meant. On the other hand, if I put something like A, again, indices, and then I might say, let's say int, where I will actually say along the way, alongside, I would say this would denote the set of 32 bits ints, for example, in Java. Right?
So just as a follow-up, like let's say they're both hypothetically total functions, right? So the top would not be feasible to be an infinite array. The bottom one could be feasible because at 2 to the 32 instead of modelable.
You really meant to say subjective. You don't really mean to say total, right? Okay, no worries. Okay, I'll write it down. Okay, so here, so if I say, okay, let's now review this very quickly. If I say A, let's say natural number and then total function, it doesn't really matter what I put here. The moment you say that A should be a total function between natural number and something, that's already not feasible because the set of natural number is infinite. Okay, not feasible already. So that's the total function. On the other hand, if I get, let's say A, natural number, let's say partial surjection. Okay, so let me write a little bit better. So partial surjection. And if I put simply this, that means I got to store all the set of infinite integers. Of course, that's not feasible, right? On the other hand, if I have A and partial surjection over here, but now I might put int, 32-bit integer. That's in theory possible because you might have a large enough, enough space to have that. All right, good. Yeah.
In the lecture, you have mentioned something called well-defined and undefined value for a couple of times. Could you give us a little review of it?
Well-defined and also undefined. Okay, sure. So when we say well-defined, usually we say well-defined expressions. Okay, let's say for example, if I have some integer division, let's say x divided by y. In order for this one to be well-defined, that means we have some result that's going to make sense. Is well-defined. Well-defined if, for example, y denominator is not equal to 0. Because if y is equal to 0, the whole thing is undefined.
Yes, I understand that, but I want you to like talk about the one on the relation operator, because I remember you said that for the image, as long as the set is not a subset of.
That's okay. That's the one you're talking about. Okay. Let's say, for example, so let's say we have R. let's say S and T. And let's say, for example, let's put alongside. Let's say S is simply ABC. And T here is 1, 2. Okay, let's say. Okay, so that means the set of all possible relations must come from the cross product of S and T. So that means only A, B, and C should be accepted as a valid first value. For example, D and E, they are not even in that, right? Okay. So let me first of all say the principle here. A valid relation contains members from S and T only. Okay, so let's see a valid relation, and then we'll go on to your question. Okay, so let's say this. Let's say we have R1. Okay, let's say we got A1, and then B2, and then A2. Let's say simple one to make the point. Okay. So now, what would be the relational image expression that's not well defined? Okay. So if I say something like R1 relational image, and now everything in the set over here must be a valid value from the first set, which is S. Okay. So for example, I might put something like, let's say, A and D. Right? A itself is a member of S, but D over here is not. The D here is not a member of the first set S. So we say that this particular relational image is not well defined. Now, versus, let me say one more thing, okay? So that's kind of about well-definedness, okay? Versus, if I say this, R1 over here, let me now put C. So this one here, you can see that the C is a valid value from the first set. It is okay to inquire about that. So now, do we have any pair where the first value is C? No. We don't, right? So this one here is well defined, so it's going to give us some valid result, which will be a set, which can be empty. Right?
Yeah, but add-on, does that same logic apply to domain restriction, domain subtraction?
The same.
Range,
The same.
Also for override.
Override as well. Yeah.
Okay, all right, thanks.
Yeah, you want to make sure the inquiry for all those relational operators, the value must come from the first set.
Okay.
Yeah. Mm-hmm.
So I just wanted to ask, so if you have, if you like get the image of some like two values, where one of those values isn't in the set S at all, and it would be not well defined.
You may not well, but yeah, that's correct.
Yeah. So like, what would the outcome be? We just like not compile or like.
I think it's more like a not compile. Exactly. Yeah. It's not well defined simply means not exactly not well compiled, right? Because not compiling, that means you actually somehow, or put it this way, let's put some Java analogy. In Java, if something doesn't compile, either you got a syntax error, you got a type error. In this case, it's more like a type error. You're putting some value that does not belong to the first set. So you're going to see some error in the rodent. Yeah. All right, guys, any other questions?
Oh yes, sorry to
That's okay.
asking question.
That's okay.
So I believe in the office hour you already talk about the procedure of like the precedence of operation for proposition, predicate, and set operator. So how about for the relation operator for the image override, domain subtraction, domain restriction, set, and so on?
I think we somehow, well, I'm pretty sure they have some set precedents. So, but I didn't want to complicate about the discussion. So I would say if you kind of get some very complicated expression, so usually I will use parentheses to really force the interpretation to help you. So you don't need to worry about precedence.
Oh, okay, great. Thank
So you just make sure you understand about, for example, conjunction, right? All the precedence you should know would be not even for quantification. So you can think about conjunction and also disjunction, implication, in negation, right? So if I got something like a not P and Q or R implies, let's say, S or not T and U, let's say, like something like that, right? So we know that this will be the highest precedence. So this one should be evaluated first, not P and also not T. All right? And then we go with the conjunction. So this one here should be the next one. And also this one here should be the next one, conjunction. Okay? And then we go with disjunction. This will be the disjunction. And this will be in the disjunction. Right? And the implication will be interpreted the last. Right? Like that. I know some of you might be from the software development stream, maybe from CS. So in which case you may have taken EECS 2001 theory of computation. So when there's something called compiler, which people implements. I think to really implement a compiler, usually you have to somehow generate something called a parse tree. In order to generate a parse tree, you have to somehow follow through the precedence to figure that out, just for your information. But if you're in engineering, you haven't done any parsing before, that's okay. Don't worry, we're not going to cover that in this course. That's okay, no worries. Yeah, we got time.
Alex, do you suggest we can try to practice or prepare ourselves for the added difficulty tomorrow's test?
Make sure you properly rested for today, right? Just it's very important before every test. That's very important. I think tomorrow you will be kept busy for the test. So make sure you kind of sketch whenever you can, just to make sure you're clear about what the question is asking. And then any intermediate result calculation, don't try to rely too much on just calculating in your mind. You want to really do something on the paper, right? And make sure you're very clear about all the definition, everything that we cover in the math review slides. So everything we're going to cover tomorrow in the test, you can definitely find them in the slides for sure, or the iPad notes. Yeah. So try the practice test. If you haven't done so, if you got any doubts about the practice test, you can definitely go to that recording for the review session and just go over the definition and then go over the lab solution. Yeah, that's all you can do. Yeah. Of course, the question themselves may be something you haven't seen before, but they're still within the coverage, right? So it's more like a typical, math course, right? Even though we're covering the same topic, but the question itself may be different, right? Yeah. Huh?
That's usually a theme, which is fine. Like where we see something we haven't specifically seen before, how can we take some concept and try to extend it to where we can notice or think of a potential twist you can add to it?
Well, I would. You mean how you can kind of predict what I can ask in the test?
At least extend our understanding more than.
Oh, I see what you mean. I think really the best way, because whenever you run into some question you haven't seen before, all you can do is go back to the basics, right? If you know that, okay, this question here is really about partial function, you want to go back to what's really the definition for a partial function, maybe about functional property, maybe it's about injective property. From there, you can see whatever definition you can use from there to solve the question, right? Go back to the definition, basically. Mm-hmm. Diego.
For time management, would you say that you will design the test so that most questions should get the same time allocated, or would you have
okay,
questions?
There will be easier question there. Mm-hmm. There'll also be harder question. So I don't necessarily think they should be allocated at the same time, but excuse me. But you can definitely navigate the question back and forth without it's not like once you move on, you cannot go back. It's not the case, right? So I would say it's not a bad idea. You spend 1 or 2 minutes just to see exactly what question you are given, get some idea, and then to decide which one you want to go first. Yeah. But I don't think because they're not equally weighted, so you may actually want to spend maybe more time on the question you're not exactly sure, right? Yeah.
When you say we should go back to the definition of things like partial functioning, do you mean as in like, oh, not everything in the domain is mapped like English, or like the actual
formal definition? Yeah, this will be another tip I will actually give for the exam. Because exam is going to be even the case, because it's going to be cumulative, so also get a data sheet, right, for the exam. So I would say if you see anything that somehow seems to be very challenging at first, think about what kind of basic concept you may have to use, and go back to the definition, formal definition for those, and then try to solve them accordingly. Yeah. So guys, I don't mind taking a few more minutes, but if you still have questions, okay, just bear with me, okay? If you got more questions, I'm happy to answer. Go ahead.
Yeah, could you do a set comprehension in the ASCII code?
The set comprehension?
Yeah.
I think it's going to be very similar to what we have.
In the ASCII code.
ASCII, right?
Yeah, because that's the one you want, right? That's the answer you want.
Okay, how about this one here? I'll just use that example to show to you, so I save some writing. So guys, the question was, how do we write set comprehension in ASCII form? Very similar to how you will write in the paper. So curly brackets separated by vertical bar. Okay, I will typically start with the right-hand side. So this part over here will be about a constraint. What kind of constraint should be satisfied in order to keep something in the final set? So here we say we got conjunction, conjunction, conjunction. So this will be the first part, second part, third part, and fourth part. So here I'm saying A should be in S, B should be in T, A is not equal to something, and B less than 3, right? Combining all those constraints together, what should I include in the final set? The format for every member in the set is going to be a pair, which will be A and B. So whatever A and B that satisfy this particular constraint, put all those combinations in the set. That's set comprehension. Okay. Yeah. So I would say the way you write set comprehension is very similar to how you do it on the paper. Very similar. Thank you so much, and I'll see you tomorrow, 1:30, Williams Small Center. Thank you.